In previous lecture we have discussed the Norwegian condensation reaction where we have used the diethyl malonate. Now the next reaction is the Stobbe condensation reaction. Here in this Stobbe condensation reaction we are going to use the diethyl succinate. The base used is potassium salt of tertiary butoxide. Okay, this is a tertiary butyl group C attached to 3-methyl substituent. So it abstracts this alpha proton. This is the alpha carbon containing 2 alpha hydrogen atoms. Not this one. This alpha hydrogen atom is abstracted by the base and carbanion is generated. Okay, and this is the carbanion generated. Now this carbanion is going to attack on the carbonyl carbon of aldehyde or ketone. Here we are using the benzaldehyde. So it is going to attack on this carbonyl carbon, which is an electrophilic carbon, and then the next compound that is formed is this one. We have written this COET in this manner, that is in vertical manner. So this is the carbon where we generate the carbanion attached to COET. Next is CH2, then this CH2 is attached to COET. So this is the CH2 which is attached to C double bond O COET. Now this carbanion forms the bond with this carbonyl carbon which is attached to benzene ring, and this becomes O minus. So here it is a O minus. Okay, then there is a just intramolecular cyclization reaction. This O minus is going to attack on this carbonyl carbon and OET leaves. So we get the cyclic product which is a 5-membered ring. Okay, then this tertiary butoxide, it acts as a base, it abstracts this proton, this electron shifted here, and again there is a ring opening reaction takes place. So here there is a double bond is formed between these two carbons, that is alpha beta carbon, and here O minus is generated. Now in presence of solvent it takes the proton and it becomes OH. Okay, so here we get the alpha beta unsaturated carboxylic acid. So this compound and this compound is same, just we have rearranged it. This is the benzene ring I have written, then this is alpha beta, so this is alpha carbon and this is beta carbon. Okay, so here this is alpha and this is beta carbon. So this is alpha and this is alpha, and this carbon is the beta carbon. Okay, so the beta carbon is attached to phenyl ring. This is the alpha carbon. See, then it is attached to CH2 and it becomes COOH. So it is a alpha beta unsaturated acid is formed. Okay, in this overall reaction, and this reaction is called as this is the alpha beta unsaturated acid. This is benzene attached to beta carbon. So this is the beta carbon which is attached to alpha carbon. Alpha carbon is attached to COET. This is CH2 and COOH. So this we get the alpha beta unsaturated acid as the product. Okay, so this overall condensation reaction is called as a Stobbe condensation reaction. In this reaction actually we are using the diethyl succinate molecule. We generate the carbanion in diethyl succinate molecule and which reacts with the benzaldehyde molecule, and the product is alpha beta unsaturated acid. Okay, now the next reaction is the Henry reaction. Here we are going to prepare the alpha beta unsaturated nitro compound. Okay, so here we generate the carbanion. Here this is the nitro compound which we are going to use benzene attached to CH2 and nitro group. Okay, so this hydrogens, these are acidic hydrogens which can be easily removed by the base. So this is again the potassium tertiary butoxide we are using as a base. It abstracts this proton and this bond is shifted here, and now it becomes O minus. Okay, so the next compound formed is, here is a benzene ring CH. Now there is a formation of double bond between carbon and nitrogen. It becomes O minus and this is O minus. Okay, now it acts as a nucleophile. So this electrons come back and this is going to attack on now the benzaldehyde molecule. Again the reaction is carried out with the benzaldehyde molecule. So we get benzene ring, this carbon attached to nitro group. So this is the nitro. Now this also forms a bond with this carbonyl oxygen, which becomes OH. So here the carbon which is attached to carbonyl carbon of the benzaldehyde, and it becomes OH, and this is the benzene ring. Okay, then base again abstract this proton, and there is a water molecule is removed. There is a formation of pi bond here, and OH leaves. So we get alpha beta unsaturated nitro compound. So here in this Henry reaction, we are preparing the alpha beta nitro compound by treating the carbanion generated from the alkyl nitro compounds with the help of base, and treat it with the benzaldehyde molecule. Okay, so this is the next reaction. Now next is the synthesis of alpha beta epoxy ester, and this reaction is actually called as Darson glycosidic ester condensation reaction. Okay, so here we are using the alpha haloester. Actually it is ethyl acetate, CH3 C double bond OET. One of the alpha hydrogen atom is replaced by the chlorine, so it becomes alpha haloester. Alpha chloroethyl acetate we are using, treat it with the potassium tertiary butoxide. This alpha hydrogen atom is removed, and the carbanion is generated here. Then this carbanion reacts with the benzaldehyde molecule. Again here the reaction is with the benzaldehyde molecule. So this carbanion, it is attached to COOT and Cl. So this is COOT Cl. This carbanion forms bond with this carbonyl carbon of the benzaldehyde, which becomes O minus, and this is the benzene ring. Okay, now this O minus is going to attack on this carbon which is attached to chlorine. Chlorine leaves. So we get the 3-membered ring is formed, 1, 2 and 3. So here is the epoxy ring is formed, and this is called as alpha beta epoxy ester. So this reaction is called as Darson glycosidic ester condensation reaction. Here we are using the alpha haloester, generate the carbanion from the alpha haloester, and then treat it with the benzaldehyde. We get the alpha beta epoxy ester. Now the next reaction is the Michael addition reaction. Now in this Michael addition reaction, we are using the diethyl malonate. So this is the diethyl malonate treated with the sodium ethoxide. Carbanion is generated, and then this carbanion, it is treated with the alpha beta unsaturated ketone compound. So it is going to attack on the beta carbon, and then this pi bond is shifted here, and this becomes O minus. So the next compound we get is, this is the malonic ester. This carbon forms bond with the beta carbon. This is beta carbon. This is alpha carbon. Now there is a double bond formed between the alpha carbon and the carbonyl carbon, and it becomes OH. Okay. Now it undergoes the tautomerism, just shift of a proton from oxygen to the carbon. So we get the 1,2 addition product, which is a more stable product after tautomerism. So this is just a addition reaction, that is called as a Michael addition reaction. Here we are using diethyl malonate, dimethyl ester, and treat it with the alpha beta unsaturated ketone. So we get the addition product. Okay, so that is a Michael addition reaction. Now next is the synthesis of heterocyclic compounds. Okay, synthesis of heterocyclic compounds. So here we are using again the diethyl malonate, and the next compound used is urea. So the reaction is between the diethyl malonate and the urea. This nitrogen contains the lone pair which is going to attack on this carbonyl carbon, and it becomes O minus. Similarly here it is going to attack on the another ester carbonyl, and it becomes O minus. So the next structure or next compound is this. These are the NH2 C double bond O. It forms bond with this carbonyl carbon which is attached to CH2. Now it becomes O minus and O minus. When it comes back, OET leaves. It comes back, OET leaves. And this, there is a loss of proton from the nitrogen atoms. Both the protons are lost, and positive charge on nitrogen atom is vanished. So the next compound we formed is this one, which are called as a cyclic urids. So cyclic urids can be synthesized from diethyl malonate and urea, and this reaction is very useful for the synthesis of heterocyclic compounds. Okay, the next synthesis is the synthesis of substituted furan derivatives. Okay, so we can synthesize the substituted furan derivative. Here we are going to use the ethyl acetoacetate molecule. Pyridine used as a base. It abstracts this alpha proton. Carbanion is generated, and then this carbanion forms the enolate ion. Okay, this enolate ion is there, and here instead of the carbanion, O minus is going to attack on alpha chloroacetate. Okay, actually it is a alpha chloroacetone. It is actually acetone, CH3, C double bond O CH3. One of the alpha hydrogen atom is replaced by chlorine, so it is a alpha chloroacetone molecule. Okay, so it is going to attack on this carbon and chlorine leaves. Okay, so the next compound form is here COAT, and this is CH, which is attached to this carbon. This is this carbon CH, which is attached to COAT, attached to CH3. Now it is O minus, which forms bond with the CH2, C double bond O CH3. Again intramolecular cyclization takes place. Pi bond going to attack on this carbonyl carbon, it becomes O minus. So here is the next compound formed, which is a 5-membered ring. 1, 2, 3, 4 and 5. Okay, so CH3 remains as it is, COAT remains as it is. Now it forms bond with this carbon and it becomes O minus CH3 CH2O. Okay, next there is a shift of, as these electrons are moved here, there is a formation of pi bond and the positive charge is developed on the oxygen atom. Okay, next is the abstraction of proton, and this electron shifted here. This pi bond moves on the oxygen atom, so positive charge on oxygen atom is vanished. Okay, so it becomes OH. The pi bond is formed between these two carbons and the positive charge on oxygen atom is vanished. Pyridine then abstract this proton and there is a pi bond is formed between these two carbons. So this electron shifted here and OH leaves, so we get the substituted furan as the product. Okay, so we can also synthesize this furan derivative by using ethyl acetoacetate by treating the carbanion of ethyl acetoacetate with the alpha chloroacetone. Just there is a cyclization reaction is there and we get the substituted furan as the product. Okay, we get the substituted furan as the product. Now next is the NOR synthesis of Pyrol. So here in this NOR synthesis of Pyrol, we are going to use again the ethyl acetoacetate molecule, treat it with the nitrous acid. Okay, HNO2, not HNO3. So it is a HNO2. So it forms the oxime, C double bond and OH. Then in presence of zinc and acetic acid, it forms NH2, C double bond O. Now undergoes the reduction. There is addition of hydrogen atom, removal of OH, so it is a reduction reaction. It forms the NH2. Now this NH2 then react with the another ethyl acetoacetate molecule. This is the second ethyl acetoacetate molecule. NH is going to attack on this ketonic carbonyl, which becomes O minus. Okay, so we are going to rearrange these molecules. Here I have started from this carbon attached to CH3 C double bond O, so CH3 C double bond O. Then here is the CH, which is attached to COAT. So here is the COAT. Then it is attached to NH. Here it forms bond with this carbon. So C, it becomes OH, CH3, CH2, COAT. So it is CH2, COAT. Now in presence of acid catalyst, it accepts the proton and it becomes OH2 positive. That is the only change. Okay. Then in the next step, the lone pair of on nitrogen atom moves here and OH is leaves as water molecule as a OH2. Okay. So there is a positive charge is developed on the nitrogen atom. All other things are remains same. Then this alpha hydrogen atom is lost. This sigma electrons moved here and this pi bond is shifted on the nitrogen atom. So here is the formation of the double bond and positive charge on the nitrogen atom is vanished. Okay. In the next step again there is a cyclization reaction takes place. This lone pair on nitrogen, it moves here and this pi bond going to attack on this carbonyl carbon and it becomes O minus. Okay, so here is a 5-membered ring is formed, 1, 2, 3, 4 and 5. So this is 5-membered ring, it becomes O minus. So O minus is there, here one hydrogen atom is there. So it abstracts this hydrogen atom, it becomes OH. This bond electron shifted here and the positive charge on the nitrogen atom is vanished. So here is the pi bond is formed. So here is the pi bond and it becomes OH. Okay, that is the only change. Then again this lone pair of electron is moved here and it moves here and this OH leaves. So there, as nitrogen gives its electron, there is a positive charge is developed on the nitrogen atom. Okay, then the this hydrogen atom is removed, this bonded electron is shifted here, this pi bond is shifted here, and this pi bond is shifted on the nitrogen atom, and we get the substituted pyrrole as the products. So in this way we have carried out the various synthesis by using this active methylene compounds, and this chapter is finished. Now in the next lecture we are going to start with the last chapter that is remaining, and that is rearrangement. Okay, so I can give the exercise on this chapter which can be posted on the Google Classroom. Okay.